presentation we're doing today is to address questions that we've been posed with from folks that they don't seem to understand what the difference is and why there are issues with in-circuit programming of serial EEPROMs. Basically, we're told that sometimes it works, sometimes it doesn't work, sometimes it works on an assembly, and the next time they try to do it on an assembly, it doesn't work. So the point of this presentation is to try and explain why that is. So I'm going to get started with what it takes to program a serial EEPROM, serial double EEPROM, out of circuit. Okay, this is what most programmers are designed to do. Okay, if you get a USB-based programmer, one of the inexpensive ones that's manufactured in China, where basically just have the programmer dangling off the end of a USB cable, and it's got a Windows program that runs it. That is an out-of-circuit programming product. It wasn't designed by the designer to program in circuit. Can you hook it up to chips in circuit? Yep, you sure can. And will you get consistent results? Maybe, maybe not. Okay, so let's address first what it takes to program a serial double EEPROM out of circuit. Okay, so what we have on the screen here is a 93C56. I tried to find one where you could read the part number, but it just didn't seem to want to cooperate with the lighting, so you're just going to have to trust me that that's a 93C56. Okay, so well, what does it take? What are all those 8 pins? What does it take to program that part out of circuit? Well, let's go to the part data sheet, and I'll just point out some things to you. These are kind of engineering things, but I know probably most people watching this are not engineers, so I'll try to keep it at a level where you'll be able to understand. And if you understand what it takes to program one of these parts out of circuit, then you'll have a better understanding of what it takes to program the part, support the part when it's in circuit, and what gives you the best opportunity for success. Okay, here we are at the a data sheet. I got this off of the Mauser website. This is the data sheet. It's a microchip data sheet on the 93 family of parts that they offer. You can see the part number 93AA, ABC, 93LC, 56ABC, 93C, 56ABC. And okay, now what does it take to program a part? All right, well, first you've got to have power applied to the part. And if you look at the physical connections to the part itself, we'll show you what those are. Okay, so let's scroll down the data sheet here, and here we are on package types. Okay, package types, not to scale. And I'll just point out a couple of other things to you. This was something else that to me was a fascinating find in the market. This is called a rotated package, rotated SOIC. Okay, except the 93LC56BX. We didn't do that one. Okay, well, why in the world would you make a rotated package? What is the point? Okay, there's only one point to taking the pins, which would normally be assigned to a standard part, which is over here. Okay, SOIC, a small outline integrated circuit, to a regular old SOIC, which is this is says PDIP and SOIC. Okay, this is what you would normally find. Okay, if you look down here, VSS, which is ground, is on pin 5, and VCC, which is incorrectly labeled. It should be VDD because these are MOS transistors in here. They're not bipolar. VCC is voltage collector to collector, and there are no collector-oriented transistors in this part. But I guess these are new graduates that did this because they mislabeled this. This is right. VSS source, but this should be VDD, drain. But anyway, that's maybe another video. Okay, but a rotated package, they put VCC on pin 2, and they put VSS on pin 7, they put the org pin on pin 8, and if you download a datasheet, and everybody's certainly able to do that, you just go online and find your part, download the datasheet, and you can see which pins go where. These, you really can't tell, okay, because you might get one with a rotated package. They're pretty rare, but you'll find them. They will definitely cause you to scratch your head and go, why isn't this working? Okay, well, basically it's not working because you're trying to connect the wrong pins to the right functions on your programmer, and it doesn't function properly. Okay, so I'll just go over these other package types real quick. TSSOP, this is the one that is wider than it is tall. They just do this for space saving. Anyway, I didn't answer the question. I think they did this for the guy that is laying out circuit boards. He needed to have pins in places that this package didn't allow as easy routing of the tracks as this package. So the chip fabricators, manufacturers, created this special rotated package, and they all make them. Microchip makes them, ST makes them. So I really don't have any more knowledge than that, but I couldn't understand why they went to the trouble of creating a separate pinout for that package. But anyway, here's the TSSOP. Whoops, we are scooting up. I'm not done here, so let's scoot down here. TSSOP is the package, as I said, it is wider than it is tall. And MSOP is even teenier. These are the ones, MSOP is a micro small outline package, and TSSOP is thin shrink small outline package. Okay? And they are, they're just smaller. So as the board assemblies shrink and the designers want smaller packages, they will respond by giving you an option to choose a package, giving that designer an option to choose a package, which will give them the opportunity to hook it up, find a place on their circuit assembly to place it where it won't take up much space, and the designer can then solve a space problem if that's what he's confronted with. This one, SOT, small outline transistor. It's not a transistor, but that's the package, okay? And the transistor, all transistors will have 3 control legs, okay? 3 control pins. A bipolar transistor will have emitter, base, and collector, and a MOS transistor will have source, gate, and drain. When you have the 3 pins, or the 6 pins in this case, you could put 2 transistors in this package. And you can also, if you have an 8-pin part where one of the pins is org and one of the pins is no connect, like you can see here, like 7 and 6, then you can squeeze that piece of silicon into this little teeny weeny package. And I'll guarantee you, when you find one of these that's a double EEPROM or an assembly, it probably will not have a part number on it that you can read. Or if it does, it's going to have a small fragment of the part number. Okay, so that's kind of information about the part, the package. Now I want to talk about, as I said, first let's talk about powering up the part. Okay, VSS is ground, or the negative part of the negative side of the power rail. VCC, which ought to be VDD, is the positive side of the power rail. Okay, so this is should be 0 volts, and this should be in a normal normal automotive module. This would be 5 volts. Okay, so that's where basically the power enters the part. All right, and this power rail is shared. It's going to be shared by all of the other components, or by the majority of the components. Sometimes the designer will split his power rail up, and he does that for reasons that his design, he's been forced because of the current requirement of the components on the module itself. But most of the time the power rail is shared. Okay, so you got your microcontroller, you've got other components that are all on the power rail and are all consuming current from the power supply. All right, that's important for you to understand. when we're programming parts out of circuit, all right, these pins, they're all alone. Current flows from the programmer into these pins, and it doesn't need to go anywhere else because there's no other component attached to this part. It's just the part sitting in the programmer. So in that case, if you have a programmer which is receiving its power from the USB port, and assuming that the guy that wrote the code in the programmer, his algorithms are correct, and he knew what he was doing, you shouldn't have any problem. Out of circuit is an easy solution to accomplish. All right, now let's talk about the other signals so you understand what those are. Okay, I'm just going to go over them one by one. We have CS here, which is chip select, and you can see here's the function, name, CS, function, chip select. Just tell you what they do. Not going to have much meaning to you, but in the engineering world, chip select wakes up the chip. Okay, you've got to have that function there. Then you have CLK, which is clock, and serial data clock. Okay, basically the clock signal is what synchronizes the data going into the part and coming out of the part. Then you have a pin called data in, DI, and this is where you send information to the part. Okay, every time you send a bit, and these are serial parts, so the information goes in, comes out one bit at a time. You send it a bit, and it's synchronized with the clock. So it's like, here's a bit, and the clock signal then will cause that bit on the data in pin to be input to the part. Okay, once you've sent information to the part, like you sent it an address, you want to get a byte out from an address that you send in. The byte that comes out is going to come out on the data out pin. The bits come out one at a time. So you got data in, data out, and you have, so this is how you talk to the part. You've got chip select, clock, data in, and data out. That's it. In the case of a 93 family part, these are your 4 communication pins, okay? And these pins, when you're communicating with the part, have to meet what are called logic levels. All right, so let's go through the rest of these so you understand, but then I'm going to talk about logic levels. Okay, VSS is ground. Okay, that's your negative supply. NC, it's an 8-pin part, but they don't need 8 pins. They only need 7. So NC means no connect, meaning don't hook anything up to it. Sometimes they use that for testing the silicon, but not always. Org is memory organization. Okay, that determines whether the data organized in the part is organized as bytes, groups of 8 bits, or words, groups of 16 bits. It does not affect the actual storage capacity of the part. It just affects how data goes in and out. Okay, if you are reading it 8 bits at a time, the org pin is going to be grounded, and you're going to give it an address that's going to specify a specific 8-bit byte, and then you're going to bring 8 bits out. Okay, if the org pin is not connected, it will be it'll go to a high level, because internal to the part there's a component called a pull-up resistor, and it'll pull up the org pin to a high level, and at that point the internal organization switches to 128 16-bit what are called words. A word is 2 bytes, and when you communicate with a part, you got to send in a word address, and you have to receive 16 bits, not 8 bits. Okay, so that is what the org pin is for. And lastly, we have a VCC, which is the positive power supply. As I said before, it ought to be labeled VDD, but they didn't. Okay, now, again, I wanted to discuss logic levels. Okay, because logic levels are important to understand when we get to the in-circuit programming aspect of double EEPROM work. Okay, so as I said before, the power supply for these components is normally 5 volts. Okay, but as you saw in the first part of this, they can run down at a significantly lower voltage. Okay. So I'm going to scroll down the data sheet here and until I get to the part that shows the timing diagrams. Okay, these are the timing diagrams. This is what an engineer uses when he has to figure out, especially the guy that's writing the software, what signals he has to generate that come out of the pins of the programmer that talk to the part, get the part to do what you want it to do. Read data out, put data in. Okay? Well, if you look here, you'll see that there's a low state, like here, and then there's a high state. Okay? This is called a logic level. All right? You have to meet the logic level specification, otherwise the part will not recognize what you're trying to, or what you are requesting it to do. All right? Well, these are the signals that come from the pins on the programmer. And when the part is in the socket of the programmer, there is no problem generating valid logic levels. Okay, so you can go from low to high and high to low, and your little USB programmer will do that without a problem. Okay, and here we showed that's the what is that? That's the chip select line is up here, going from low to high. Clock line going from here low to high. Here's the kind of stuff you might find interesting. Here's your data in line. The clock signal is synchronizing this particular, either you're clocking in a 1 or you're clocking in a 0, and the data out. The clock will, on the falling edge of the clock, you'll get your data coming out. Anyway, the point I'm trying to make here is that these levels are very, very important for successful operation of the device. And when you use the device by itself, isolated, there's no problem, okay? Because whenever you have information that's going into the part, you have a voltage applied, and then even though they don't show it here, there's a little teeny weeny amount of current that has to be consumed by the part in order for this voltage to be recognized. Okay, well, these are CMOS parts, so they don't draw hardly any current. Okay, so you don't have to worry about the pen drivers on your programmer being able to source sufficient current to get, you know, the logic levels to be valid. Okay, so you go from 0, you go to 5. Some programmers give the ability to drop this down, but that doesn't always solve a problem for you. Okay, so when you're out of circuit, hey, not a problem. You can do you know, any part simply because the component, the leads on the part itself, are not going to consume enough current to cause an issue. Okay, so we talked about out-of-circuit programming, the easy stuff. Okay, where you don't have to really worry about dealing with other variables in the programming equation. Okay, you're powering the part from the programmer over the USB cable. The programmer generates the highs and lows that are required to communicate with the part. Part responds, and the programmer can read the data coming out, and everything is just dandy. Okay, which is why you see in a lot of videos guys unsoldering parts, and they drop it into the socket on their programmer, and they read and program, and then they resolder it to the assembly. Well, that is hardly convenient. So let's look at what is required for the best opportunity for successful in-circuit programming. Okay, this is an ECU out of a Toyota of some type. I don't remember which one it is. Could be a Camry. Not important, because I just want to point out, I want to start the in-circuit programming aspect of this presentation by showing you this has 3 processors, 1, 2, 3. Each one has its own crystal, 1, 2, 3. And each one probably also, not probably, definitely has its own function. Okay? Engine control, climate control, other things. I mean, the guys that designed the module, they put 3 processors with 3 functions on one circuit assembly to keep costs down rather than having 3 modules. But anyway, this processor has associated with it this 8-pin part. Sorry for the glare. We'll take care of that in a moment. That's a 93C56. So let me zoom in so you can see it, because it's important that you see why the the issue of in-circuit programming becomes a little bit more inconsistent in terms of the result. Okay, I believe you can see that this is the far left processor, and you can see that the serial double EEPROM, it says 93C56. Okay, and the 93C56, as we described in the previous part of this presentation, has those control pins. Got power, okay, and I'll guarantee you on this module that the power for the 93C56 is shared with this processor. Okay, so the processor, the 93C56, and other components on this assembly are all tied to the same power rail. Well, also, if you look closely at the pins on the 93C56, I don't think I can really look at the left-hand side. I'll try to show with the pencil here, but I'm not sure I can get it close enough for you to see. You can see tracks. They go over to these little resistors here, and then the resistors go over to pins on the processor. Okay, so what that means is that the processor is controlling the 93C56. Well, you kind of expect that because that's where the information is stored that the processor is going to need to access. Okay, so the processor, in a normal operation of the module, it's reading and writing information to the 93C56, and it's using its I/O pins. Okay, and that's why you'll see on modules, you'll see these massively huge components with all of these pins on all four sides. Why are all of those pins there? Okay, well, those pins, if you're managing the various aspects of a vehicle, you've got all kinds of information that's coming in and all kinds of information that you want to be putting out, firing injectors, reading crankshaft position, all of that, and that takes pins. Okay, and that's one of the reasons, and I've addressed this in some of our other videos, why the engineers like the little 8-pin serial double EEPROMs. Okay, because if you needed to use a regular double EEPROM, which would be a parallel part, you'd have lots of pins that would be necessary in order to control it from the processor. Well, with a little 8-pin part, you don't need that many. You need power, and in the case of this 93C56, you need a clock, chip select, data in and data out, and that's it. So it only takes 4 pins on the processor in order to read data from this part and put data into the part. Okay, so the engineers that design these modules love 8-pin double EEPROMs. Not just the 93 family, but the 25 family, the 95 family, 24 family, and so forth. But the point I want to make in showing you this is that this part is connected to other things on this assembly. And the other things on this assembly are what cause in-circuit programming to be a bit more difficult to reliably accomplish. Okay, and the reason is that whenever you have a well, let's talk about the 4 things that you need to have happen. Okay, in order to have successful in-circuit programming. Okay, the first thing you need to have is you need to have power to the part. Okay, so let's say you're doing it with a clip. You've got a clip hooked to your programmer, and you put the clip on the part. Well, what do you think happens when you tell the programmer to read the data from the part? Okay, well, the programmer does not know that you have the clip attached to a component in circuit. It thinks it's, happily thinks that this part is magically disconnected from the assembly, just like it would be if you unsoldered it. And at that point, it powers it up. Well, what happens when it powers it up is it powers it up all right. It powers up as many things on that power rail that are attached to it. Okay, so in this case, I believe, although it didn't confirm it with an ohm meter, you power up the 8-pin double EEPROM. You power up the processor. You might power up, I think these over here, I can't see them. The components to the left of the processor are probably injector drivers, but I don't know that for a fact. So my point is you're powering up a whole bunch of other stuff on this assembly. Well, if your programmer is powering up basically the fundamental circuitry, in this case an ECU, and it's doing it over the USB port, Okay, well, where does the USB port get its power? It gets it from the computer. Well, up through USB 2.0, the most current that you could consume, could draw from a USB port, was 500 milliamps. Okay, well, maybe that's enough. Maybe it's not. Okay, well, if it's insufficient current to power the module, either the programmer is going to do what's called current limit, okay, where it protects itself and doesn't burn up, or if it's a cheap programmer, it'll just burn up. And the other thing that most people are not aware is that whenever you have current that flows over a wire, you get what's called voltage drop. So you may have 5 volts that's coming out of the computer, but by the time it gets to the end of the USB cable, it may not be 5 volts. It may be less. It may be 4.8. Then you start consuming more current as the module attempts to power up via the programmer, and it might drop even more. You don't know. Okay, so that in and of itself can cause issues with in-circuit programming simply because you don't have sufficient current in order to power up effectively the module. Okay, so that's the first problem that you face with the in-circuit programming, is that you have to be able to have enough voltage, okay, and enough current in order to not just power the double EEPROM, but also not have the other connected components adversely affect the next subject that we're going to cover. Okay, and the next issue, number 2, are the control signals. Okay, well, with the control signals, when it's out of circuit, everybody's happy. You got highs and lows happening, and there's no problem. Well, when it's in circuit, as you can see with the pins on the 93C56, they go to pins on that processor. Okay, and those pins on the processor are not exactly nice high impedance, I'm not going to cause interference kind of termination points. Okay, so if your programmer does not have pin drivers which can supply adequate current to the pins on the double EEPROM, basically it will not be able to override the load that's placed on those pins from the processor to which those pins are connected. And if that's the case, then you will not get valid logic levels. And if you do not get valid logic levels, you will not get data out of the part, or you'll get, a sputtering, inconsistent operation. Okay, so the programmer itself has to be able to generate sufficient current from its pin drivers in order to, one, overcome the load that is going to be present from the pins on the processor, and still be able to drive the pins on the double EEPROM to valid logic levels. Okay, so that's another issue when it comes to inexpensive programming products. And I'm not bashing the inexpensive programming products. Okay, they're fine for what you pay for them. They work. If you can buy something on Amazon for $15 or $20 and you want to, unsolder the part and drop it into the socket, go for it. But when you try to do in-circuit work, there are other variables that cause those kinds of products to not operate, consistently. And that's the point I'm trying to make here, so that people are aware of what those issues are. Okay, so driving the pins that are already attached to something from the double EEPROM, that's issue number 2. Power is number 1. Driving consistent logic levels of the pins on the double EEPROM is number 2. The third problem is, okay, let's say that we get data going into the part, but the part is responsible for sending the data out, comes out of the data out pin, as we discussed earlier. Okay, so the data out pin, you don't have any control over how much current the data out pin can deliver. Okay, the data out pin is going to go to a pin on the processor because the processor is going to be reading data from the part. But you want to read the data from the data out pin while it's attached to the processor. Okay, well, what that means is the sensing circuitry in the programmer has to be sensitive enough to pick up whatever logic levels the little teeny 8-pin double EEPROM can generate. And it may not be right up to a valid logic level. It may be below that. Hopefully it's not. If there's too much of a load because you're relying on the part to do the presentation of the data, you have no control over it. And if the part can't present the data, then you won't be able to sense it. But the sensing circuitry in the programmer needs to be sensitive enough to be able to pick up the data which is coming out of the data out pin. Okay, so that's the third issue to which you have to contend, is the programmer's got to be sensitive enough to be able to, even though you're driving all your logic levels to, or all your pins to the appropriate logic levels, the programmer needs to be able to pick up the data that's coming back out of the part after you get the request going into it. Okay, so that's issue number 3. The last issue number 4, is the processor itself. Okay, we've talked about the processor loading and how the loading of the processor will cause the logic levels to perhaps not be what the specification requires. But the other thing that happens is the voltage you're applying to the double EEPROM back feeds into the assembly. The processor may start to run. Okay, if you watch our video on the Toyota Sequoia, you see it happen. Okay, well, if the processor starts to run, what does the processor do? It's running its program. Okay, so when it's running its program, what's it going to do? It's going to go out and it's going to try to access the double EEPROM. Okay, well, what's happening simultaneously while the processor is trying to access the double EEPROM? Well, the programmer is trying to access the double EEPROM. Okay, so you've got two sets of information for one part. And what that results in is something called data collision. Okay, basically you say, the programmer says, I'm going to read the part. And it turns on the part and starts to read it. Meanwhile, the processor goes, oh, I have power, so I'll start to read the part. Well, you can get data that results in basically two sources of information trying to access the double EEPROM simultaneously. The processor and the programmer. Okay, and what can happen is the double EEPROM then becomes confused. It has a little circuit inside called a state machine. And the state machine, basically it decodes the incoming request, those bits, and then it processes those, and then it responds appropriately. Well, if the bits coming in don't make sense, if chip select goes away right in the middle of a read or something like that, you'll end up with a confused serial double EEPROM. And the confused serial double EEPROM, this doesn't damage the part, it just causes the data not to be correct when you read it. You can tell because you read it, and then you'll see these programmers will go, oh, read it, and then verify it. Okay, well, you want to just be sure that the part didn't screw up the second time? No, you want to verify that the processor, at the first read, you see stuff come out, and the second read, the stuff is different. Okay, well, it's different because the processor basically was trying to access the part at the same time the programmer was, and the data got garbled. And at that point, if you just read, you don't know that. If you just read it once, you don't know that. So you can read and compare and have a reasonably good, be reasonably certain that you got good information out of it. But what has to happen, and this is important for in-circuit work, okay? What has to happen is, in order for the part to be read with the processor attached, in order for you to read it successfully, the processor shouldn't be running, okay? For reasons that I just described. All right, well, the processor will have, as part of its startup circuitry, something called power on reset. Okay, power on reset will not allow the processor to start until its operating voltage is sufficiently high so that it can leave the reset condition and start running the program that makes the thing be what it's going to be, the engine controller or whatever. Okay, well, the best solution, or the solution to that, is to reduce the voltage to the assembly. And when you reduce the voltage to the assembly, you do that through the connection to the double EEPROM. And hopefully you'll get to a point where the double EEPROM will still be capable of responding, but the processor will not. Okay, and that's why if you just set your programmer, and the inexpensive programmers, they will output 5 volts when they're trying to read the part because they don't know the part's in circuit, and the 5 volts will flow into the power rail of the assembly, and the processor will come to life, and the double EEPROM and the processor you'll get data collision and doesn't work. Okay, so that's another issue that you need to contend with. So I will also just give you another piece of information. The 93 family, which is this part that we're discussing here, it has commands that you send it. All right, and basically when you send a command, you're sending it, a series of ones and zeros. Matter of fact, let me just show you. I'm going to go back over to the computer screen and I'll show you this. All right, let me go. I think it was down here. Okay, if you're the guy writing the code for the to communicate with the double EEPROM, these are the commands, or as they're described here, instructions. Okay, I don't want to get into the details of these unless you guys want to write code to talk to double EEPROMs. But look at the first one, erase. This is one I wish they would have never put in. Okay, because if you get data collision and you get a combination of bits, one coming from the programmer which might tell it to read and another coming from the processor which might be telling it something else, and you get an erase command, poof, your data's gone. It will erase the data at that address. Okay, and if that happens, there's nothing that you can do. Basically, the byte that was there is gone. So you have to be very careful that the processor doesn't start running and you get data collision, because I can tell you that you do this with a sob sim, you run a sob sim at 5 volts and try to read it, the data collision that happens will cause that part to become corrupt. And this is how the 93 family, one of the issues that you have to contend with. So you want to be sure, and at least with our product, follow the right procedures so you don't end up getting a data collision, which will cause your data to become corrupt. Okay, so also the 93 family is the only one that has this. The 25 family, 95 family SPI, the 24 family I2C does not have an erase command. Okay, but the 93 does. So just letting you know that. So something else for you to be aware of. Okay, so that pretty much wraps up what I wanted to cover in this presentation. I hope it answers the questions of all the people that asked about out-of-circuit programming and circuit programming. Andromeda Research has been dealing with double EEPROMs in circuit for many, many years. And we have a really good success rate. No product is perfect, but we do a really good job of working with parts in circuit. And we have kind of evolved our InCircuit interface and InCircuit software and the pen drivers that we use, so that if you use our product, you will have a pretty good opportunity for successful InCircuit work. All right, last thing I'm going to do is some InCircuit work, and then we're going to be done. So I'm going to go back, and I'm going to go over to the, let's see, what do I want to do here? Let me read the data out of the double EEPROM, which is in the module that I just showed you. So go to the overhead camera, and I'm going to take the AccuTouch probe and I'm going to put it over the top of the part. Like so. And I'm my fat fingers are in the way. Switch back to the computer screen. Press G for get valid data. And there's the information, read InCircuit from the Toyota ECU. Okay, that wraps it up. If you want to see us do other InCircuit stuff, we have videos that are on our website where we do Chrysler modules and the Toyota Sequoia and others. But I hope this addresses your questions. And again, if you like the content, we would ask you to press the like button. You can subscribe to our channel if this is the kind of stuff in which you have interest. Again, that wraps it up. And as always, we have information on our website, and would appreciate your business if you would consider purchasing or acquiring one of our products. So as always, we thank you for watching.